All right, thank you very much for the introduction, and thank you very much for Boumediene for organizing this and inviting me. I'm very sorry I wasn't able, because of some personal commitments earlier in the week, to come here before now, but I guess better late than never. And so, yeah, what I'm going to talk about today is an algorithm that delivers an exponential speedup in the rigorous learning of elliptic solution operators, and some applications of it to reduce order modeling in computational fluid dynamics. Good. All right, I mean, I can just do this. So the method that I'm going to present that is joint work with Humano Ohadi at Caltech, and so meanwhile this has been accepted to CISC. And I'll start by presenting the sort of setting for the for our rigorous results that I'm going to talk about, and then there will be some. Still, sorry, surprised that it doesn't. Oh, now it does work. Oh, it's just a delay. I see. And then, as always with things in applied mathematics, right? You have a certain setting where you have these rigorous results, and then oftentimes things tend to work surprisingly well, even though slightly outside of the setting. But so this is going to be the setting in which you can actually prove our theorems. And so the idea is that we have a domain omega in Rd, something like this, that is Lipschitz with Lipschitz boundary. And we're looking at a linear elliptic PDE. So what we mean by this is we mean an operator from H0s to H minus s that is continuous, symmetric, positive, and local. And so one example of this would be something like this Euler-Plaschen, but really this allows even for rough coefficients in the PDE, arbitrarily high order, and so on and so forth. And then we can define as G the Green's function of this elliptic operator, which is basically the inverse in the sense of convolutions with Dirichlet, so zero boundary values. And that's how such a Green's function would look like typically. So for one particular value x that we plug in, that's how this would look like as a function of y. And now for all, when we do numeric analysis, right, we need to somehow work with some kind of discrete object because we want to compute. And so there are two types of discretizations that I'm going to cover in this talk. And the first is a discretization where if we assume that the order of the PDE is larger than the m dimension, meaning that the solution space embeds into the continuous functions, then we can discretize our Green's function, so our solution operator, simply by throwing down a bunch of points in the domain and evaluating the Green's function in these pairs of points and to form a matrix, what we would call the Green's matrix. If this is not true, then we need to think of some other types of discretization. So for instance, one type of discretization that we could use would be some sort of subdivision-based multi-resolution scheme, like AHA, but it's not important that this is exactly sort of self-similar, just any type of subdivision-based scheme that we then sort of orthogonalize in this way would be fine. And so for instance, if we have access to our elliptic solver through an existing code, what we could also do is we could take, let's say, the basis function that this code works in, so for instance, like some finite element basis function, and we could use that to reconstruct a HAR-like sort of multi-resolution scheme. And so, of course, the details of how you would do that in practice depend a bit on what discretization exactly the object that gives you your elliptic solution operator, what discretization that code would be using. Now, the problem that we are interested in is how, by choosing a set of right-hand sides for this elliptic PDE, we can, and then applying this matrix theta, so the discretized solution operator, to these right-hand sides, how we can do this in such a way that we can construct the solution operator as effectively as possible from these matrix vector products with the solution operator. And so the name of the game is choose as few right-hand sides as possible. So use as few invocations of this solver that we assume to be given in one way or another in order to reconstruct the solution operator as accurately as possible. And so one can wonder why one would be looking at this. So one possible motivation is certainly the most du jour application is probably the question of sample complexity of learning PDEs from solution pairs. So if you're somehow able to observe sort of solutions for different inputs of such a PD operator, then how can you use it to reconstruct the actual operator? And so one thing that of course has made this question very interesting was the recent furore of deep O-net and Fourier operator in like much more complicated nonlinear settings where they proved surprisingly well. And so the question is, can we at least in these like very simple settings understand rigorously how well we can do? And the other application which I'm currently working on right now is also for inverse problems, where we could say that maybe we can basically use such a scheme to first reconstruct the full, let's say, Neumann-Dirichlet operator, and then just question, sort of afterwards use that sort of surrogate model as a way to do a usual inverse problem estimation. So in some sense, being able to estimate these operators will automatically put like an upper bound on the sample complexity of the underlying inverse problem. And finally, I don't know, there could be the case where you have a legacy solver that you really, really like, but at the same time it's slow or non-parallel or whatnot, and then you can maybe extract a more amenable representation in terms of these theta matrices. Admittedly, I mean, that's a more hypothetical context, but I mean, I guess that's there could be situations arising like that. But probably the main motivation really is this first point. And so related work, so that has been, again, recently there's been a lot of interest in these kind of questions. And most of the first works was based on, in some way, on the eigen decomposition or like spectral decay of these solution operators. And the downside of this is that this locks you in these like polynomial in 1 over epsilon types of complexities, because the spectrum of elliptic operators only decays algebraically. And at the same time, through actually much earlier work, there was always this kind of idea that maybe we could do better, and due to this peeling algorithm, due to Lin et al., that says that one can reconstruct hierarchical matrices efficiently from matrix vector products. However, the problem is that even though we can approximate elliptic operators well with hierarchical matrices, they're not exactly hierarchical matrices, and so far no one was able to really, and at least at the time, the authors were not able to rigorously control the approximation error happening there. And so that leaves us with some like hopeful approximation based on these techniques, but that was not able to be proven. And then the first sort of attempt at rigorously controlling the error in these type of algorithms was due to Boulay and Townsend, and I see Nicholas is in the audience, which was the first sort of way of rigorously tracing the error of these type of reconstruction schemes. However, the limitation was that on the one side, it was still having a polynomial requirement of the number of matrix vector products. And secondly, that it depends on this quantity gamma epsilon for which there are no a priori bounds. So in that sense, it's not a rigorous cost versus complexity trade-off in the limit of epsilon becoming small. And then I want to point out that after our work, they were able to improve this to remove this sort of annoying epsilon to the minus 6 term, and also and get to a logarithmic sort of polar logarithmic complexity here, although still involving a gamma epsilon term that is not bounded yet. And so our result is that we say we only need log to the d+1 matrix vector products in this sort of like discretized world. And so, in fact, even by one logarithm better than what one could have hoped for based on the hierarchical matrix approximations, and a near linear amount of computation to get an L that would be a sort of Cholesky factor that approximates this matrix theta up to error epsilon. And by setting n of the order of poly 1 over epsilon, this gives us this rate of log to the d+1, which is, again, even one logarithm better than what one could have hoped for based on the H matrix approximation. And so the main ingredient for this algorithm is a sparsity of Cholesky factors. So that's what I'm going to walk you through now. And so the prior work we had shown that even though these matrices theta are dense, their Cholesky factors are actually very close to being sparse. And so there are multiple sort of course, like a sparsity of a Cholesky factor depends on which ordering you use or which basis you represent the matrix in. And so I walk you basically through two sort of examples of such bases or orderings that lead to these sparse Cholesky factors. The first way of ordering this, so this is in this first setting where we are thinking of this matrix theta as being given by sort of pairwise evaluations of these points of the Green's function in different pairs of points. So in this case, reordering the rows and columns of the matrix amounts to reordering the points. And so the way we can order them is that we keep selecting the points successively that is furthest away from the points that we have already selected, the so-called maximin ordering. So that is the first sort of type of discretization that we are considering. And then in this case, it turns out that we can, up to very good error, we can approximate, we can set the entries of this Cholesky factor to 0 outside of a sparsity set that's constructed as follows, which is that each time when we are selecting a new point, we take the distance to the nearest point that was selected before, and then we multiply this distance with some like oversampling parameter rho. And now as we add more points, and then we add only the entries that are within that oversampled radius to our sparsity set. And so as we add more points, the later points, they will have a nearest neighbor that is closer to them, and so this radius shrinks, and so the number of non-zeros per column will go to 0. So that's the first, and again, this was like something that we proved earlier, that it turns out that up to exponentially small errors, the Cholesky factors of these Green's matrices are sparse according to this sparsity pattern, where the error decays exponentially in this tuning parameter rho. And now one can do something similar in this wavelet-based thing, where now instead of ordering from the furthest point to the more nearby points, we are ordering the degrees of freedom from the coarsest scale of the wavelets to the finer scales. And then what we will see is that in the Cholesky factor, if we now we can interpret each column of this Cholesky factor as a function again. And what we see is basically that the columns of the Cholesky factor that correspond to the bigger wavelets or the coarser scales, and they will be sort of big, like wavy, smoothed out wavelets that decay exponentially on the same scale. And then as we move to sort of finer wavelets here on the left, then we will see that the resulting sort of columns of the Cholesky factor also, again, look like sort of smoothed out, but exponentially fast decaying versions of these wavelets. And I want to very briefly give an explanation for where this phenomenon comes from, because traditionally we think of sparse numerical linear algebras. We start with something sparse, and then we do Gaussian elimination, and we have to work very hard for it to stay sparse, rather than starting with something dense, and then doing Gaussian elimination, having it become sparse. And so the reasoning is that if we were to view this X as a Gaussian process with covariance matrix theta, and we take one step of Cholesky factorization, the quantities showing up are actually the conditional covariance and conditional expectation of that Gaussian process. And so in other words, any conditional near independence of this Gaussian X is going to lead to sparsity in the Cholesky factors of the covariance matrix. And so this is like the sort of underlying phenomenon why you have this sort of, basically you should think of this Gaussian elimination now that you're conditioning on the coarse scale degrees of freedoms, and then the stuff that remains is only locally correlated. And that's the reason why we see these sparse Cholesky factors of these otherwise dense matrices. And so the intuition of having this kind of coarse to fine sparsification that was observed empirically before in the spatial statistics literature under the name screening effect, but using and extending tools from numerical homogenization, we were able to prove that rigorously. So that is just to say, these Cholesky factors are sparse according to the sort of, in this ordering and according to the sparsity pattern that I've just described. And now, so that was mostly the work that was done that we did before that. Now what we want to do is we want to use the sparsity in order to construct these Cholesky factors, not just from entry-wise evaluation, but from matrix vector products. And the first main idea is if we want to have these sort of logarithmic complexities, we somehow have to do something that is better than the SVD, which is sort of the best low-rank approximation. And so that means that we somehow have to be able to get more than k matrix vector products for the price of k matrix vector products. And the mechanism for doing this, and that was in a different setting also explored by Lin et al., is this idea of graph coloring, where we can say if you have a sparse matrix that has a known sparsity pattern, and we're able to identify columns that have disjoint sparsity pattern, and then we can choose a right-hand side that selectively activates only columns that have this disjoint sparsity pattern. And then we get all their non-zero entries conveniently written into the output vector. And so that means that we get 3, like afterwards we can pull them apart, and so we get 3 matrix vector products for the price of 1 in this case. And now what was important for us is this actually turns out to also work for Cholesky factors. So if you now have a Cholesky factor where the leading columns are sparse and with disjoint sparsity pattern, we can do the same thing to recover the non-zeros of these leading 3 columns of the Cholesky factor. And now geometrically the way this looks like is that we would use a right-hand side that in this sort of spatial sense uses these like spatially separated pulses. And then in the Cholesky world, these spatially separated pulses become almost sort of like disjoint pulses. Because of this exponential decay, there's a bit of an overlap, but basically by paying a little bit more, we can always like make sure these pulses are a little bit more away from each other at the cost of needing some more matrix vector products for the same number of right-hand sides. And then what we do is we just, with like cookie cutter, we cut them out, and each of them becomes its own sort of its own column of the Cholesky factor. And so in this example, we would be able to get an approximation of 16 columns of the Cholesky factor at the price of just 1 matrix vector product. And now the problem is that we have these big fat wavelets sitting in the beginning, like the core scale wavelets that have support with everything. And so we somehow have to be able to prevent them from polluting our measurements of the finer scale wavelets. And the way we're doing this, again, this is an idea that in a sort of in similar spirit appeared in the Lin et al. Paper, is that we first identify them and then subsequently we just subtract them from our matrix vector products. So right, we compute the matrix vector product with our right hand side, and then we subtract the matrix vector product with this outer product here of what we have already identified. And that allows us to sort of reveal this like nice and sweet sparsity that sits on the finer scales of the factorization. And this basically, the resulting algorithm kind of looks like maybe not so surprisingly, like a Cholesky factorization, where basically each time we're doing sort of basically doing a left-looking update, and then that reveals a new sort of column that contains the values of a bunch of new columns of our Cholesky factor, and then we apply this scatter operation that again like does this cookie cutter thing of cutting out the individual new columns of the Cholesky factor from this one sort of result that we get from our matrix vector multiplication. And there is also a non-symmetric. In principle, we can straightforwardly extend this to a non-symmetric operator, so to have like an LU version of this. However, then we need adjoints or adjoint matrix vector product. I think that's also what, at least from the abstract, what Nicholas was, I think, talking about earlier in this symposium. Now, the main challenge is actually how to control the error propagation. That was also the main challenge for these hierarchical matrices. In some sense, it's even worse for us, because if you naively look at this Cholesky type operation, it's basically like it's a column by column by column operation. And so in principle, at each time we're doing this, we're doing one elimination, we get a sort of an error on our Schur complements, and so we have to apply for to do our theory, we would have to apply some kind of like Schur complement error bound. And it turns out that these Schur complement error bounds, they are multiplicative. And so the problem is then basically for every single of these eliminations, we would have to apply our Schur complement error bound. And so we would get an error that sort of grows exponential in the number of eliminations. And that would offset all this nice exponential decay that we have as we're increasing the factor rho. And so the trick really is that we are grouping degrees of freedom. So instead of eliminating, let's say, all these orange points in a row, what we instead do is we slightly expand our sparsity pattern and say that now basically all these points interact with all the points that are sort of among the maximal interaction radius. And then what we can do is we can relate our element-wise elimination to the block-wise elimination that we do here. And that means that for each of these blocks, we only have to apply our Schur complement error bounds one time. And so that allows us to drastically reduce the number of times we have to invoke these perturbation bounds for Schur complements, and that allows us to bring this error from some gamma to the order n to gamma to rho to the d. Okay. There are some further outcomes that I write. So maybe I just move directly to the some numerical experiment. So I mean, right, we can apply this now directly to. So this is the same example in the Lin et al. Paper, and we see nicely that as we increase the rho, whatever our the error goes down exponentially, which is sort of predicted by our theory. But and so, for instance, we can recover this 200,000 by 200,000 elliptic problem from about 2,000 matrix vector products. Something that I found more interesting, because it shows you something that our theory does not already say, is that this also works for fractional operators, which is very mysterious, because you would think that since in fractional operators, even the differential operator is not local anymore, you would think that somehow it doesn't work. But somehow I have some intuition that I'm willing to share if you ask me afterwards, but it seems to work for fractional operators basically unchanged to the ordinary case, which I think is also possibly one very useful application to use this for efficiently applying solution operators of fractional operators. Then, so we also have like non-uniform meshes, but I want to briefly close by showing what's maybe a more interesting application, which is an application to reduced order modeling in fluid dynamics. And so this was a collaboration with my colleague Spencer Bryngelson and then Ali Mani and Jesse Liu at Stanford. And so what Mani's group had been working on was a so-called macroscopic forcing method. And so what this macroscopic forcing method basically does is it solves a Navier-Stokes equation over a long time interval. Then it sort of averages along the time axis the result, and maybe along one of the spatial axes, it averages the result according to some of the axes. And then they're looking for a advection diffusion equation that sort of replicates the solution. And it turns out that the key object in this sort of coarse-grained advection diffusion equation is the so-called eddy diffusivity operator, which is the sort of non-local diffusion operator that arises from the Schur complementation, from the averaging out of of some of the degrees of freedom. And so this macroscopic forcing method is able to get matrix vector products, and with some extension that we did matrix transpose vector product with this diffusion kernel. And so we thought, okay, if you look at this, this kind of looks like a solution operator of an elliptic PDE, and so we might as well try our method on it. And it turns out that this works actually pretty well, where we can sort of show improvement both in terms of like the relative error and also qualitative improvement in terms of how accurately this reduced order model that we capture for a given number of matrix vector products, which are now a given number of expensive, long-running Navier-Stokes solves, how well we can use this given budget of computation to get an approximation of this sort of coarse-grained model. And so that was some laminar steady state flow, and then we also have another example with a turbulent channel flow, where in some ways we see even bigger results. Of course, like in terms of theory, this part is all like way beyond what we have any theory about. It's just, again, it's one of these things where one then takes a leap of faith after one has done the theory, and sometimes things work reasonably well. So summary, we have this exponential reduction in the number of matrix vector products to reconstruct elliptic solution operators, 2,000 matrix for 260,000 DOFs, and this seems to work well in actual application problems arising in CFD. And with this, I'm happy to take any questions.